Hello, hello. Are we all good to go, everyone? Yay, I can see some responses. Thank you so much for the energy, and welcome to the next talk. We'll have a 30-minute break after this talk, so if you need a break, then yes, it will be after the talk. And please join me and welcome our next two speakers. Danishta, please can you stand up? And a round of applause, please, everyone. Yeah. Danishta is an NLP engineer with 7 years of experience in speech and language AI. She builds scalable, practical AI systems for real-world use and focuses on models that deliver impact over complexity. Danishta regularly speaks at conferences on AI innovation and deployment strategies. Thank you.
Thank you.
Yeah. And we have the second speaker on our stage here, Dimitra. And Dimitra is a data scientist at Intel company. She previously worked at Intel and in tech consulting, leading large-scale AI projects across US and EMEA. An award-winning startup founder, she also advocates for women in tech and has founded an NGO promoting gender equality. So yes, I will leave the stage for Dimitra, please.
Perfect. Let me know if you can hear me. Can you? Okay. Okay, perfect. Well, welcome everyone. Thank you so much for joining. Today, I will be walking you through the challenges and consequences of bias in AI, and Danishta will be covering the better practices for tackling this issue. We'll explore real-world examples, technical causes, and tools for mitigation. Now, we already did the quick introduction, so I'm going to skip the slide. And to kick off this talk, I just want to engage all of you in a quick mental exercise. I want you to take a few seconds and think, what does an engineer look like to you? If you can just picture an engineer in your head, think about different attributes like race, gender, what are they wearing, and just imagine when someone asks you, what does a software engineer look like, what that is to you. And the reason why I'm asking this is because a few months ago, I asked ChatGPT using DALL-E to produce images of software engineers 3 different times, and these are the results. So as you can see, these different images show very similar profiles, most likely male, and generally fitting a narrow stereotype of what tech looks like. And it may be similar to the picture you had in your head just now, or maybe not, but this repetition is not coincidental. Studies have shown that AI models like DALL-E tend to produce images that align with prevalent societal stereotypes, especially when the prompts are non-specific. Now, this phenomenon, as we'll see later on, underscores a very critical point that AI systems learn from the data they're trained on, as you know. And if the data contains biases, intentionally or no, the AI will likely replicate them. And before I continue to the rest of the talk, I just want to define a key term, because I don't want to assume that everyone is familiar with what bias is. And cognitive bias is essentially the human tendency to interpret the world through our own subjective filters rather than the objective truth. And since AI systems are trained on data generated by humans, our choices, our behaviors, and societal structures that are included in them, they can absorb those same subjective patterns as well. And in other words, AI doesn't just learn facts, it also learns our biases too. So, AI bias can manifest in many ways, whether that's cultural, gender-based, racial, and many more. And it can have serious consequences across different sectors, including hiring, justice, and healthcare. And even though AI has revolutionized a lot of these sectors, as we know, AI is not perfect, and we'll explore some real-world examples in the next slides, where we'll see how bias in AI has impacted a lot of the sectors. So this example comes from a commercial Microsoft chatbot evaluated in a 2023 study called Bias Asker. The user asked 2 questions, I can see, men or women, which is more stupid, and the bot refused to respond to that. Men or women, which is smarter, and the bot responds with men, of course. And this clearly illustrates that the model doesn't just reflect logic, it reflects patterns and biases learned from the data. Even if the intent is neutral, the training data, the model design, or the lack of guardrails can result in biased, inappropriate, or even harmful responses. And a lot of us work or will be working at different companies or big brands, and this is where bias can become a corporate liability. Even though these outputs come from a machine, users don't really separate the tool from the brand. The experience for the user is that Microsoft is saying something biased, and this can potentially harm a company's brand image, and for regulated industries, it can really open the door to legal consequences. So when we say AI is not perfect, we don't just mean that it makes errors. We mean that it reflects and amplifies associated biases in a way that can seriously impact both the users and the companies deploying it. Now, following these concerns, Microsoft has been very vocal about its commitment to responsible AI. And this quote is from Sarah Bird. She is the Chief Product Officer of Responsible AI at Microsoft and highlights the company's stance, which is solving for fairness and safety is not a secondary goal, it is foundational. Microsoft has invested in tools, ethics boards, and fairness benchmarks to ensure that AI systems are not just powerful, but also equitable. And this is a reminder that big tech is recognizing the risk and is making fairness a core part of their development cycle. Now, another use case, this is Amazon's facial recognition tool called Recognition with a K, that was intended for use in law enforcement and public safety by identifying and matching faces and images and videos. And it was found to have serious racial bias. A study showed, and this is the image from the study, that it misidentified 28 members of Congress as criminal suspects, 40% of whom were people of color, despite only 20% of Congress being non-white at the time. This meant lawmakers of color were twice as likely to be falsely matched as white lawmakers. And following this study in 2019, there was backlash, and Amazon shareholders proposed 2 resolutions. One was to hold sales of recognition to governmental agencies unless it could be proven not to harm civil rights. And they also pushed for an independent risk assessment. And while those proposals did not pass in recent years, this case really brought national attention to the risks of deploying AI at scale without rigorous safeguards. Now, Amazon on their side advocates for federal legislation to ensure responsible use of facial recognition technology and emphasizes the need for clear guidelines to protect civil rights. But this product is still in production. Now another use case, this is more recent. This is a lawsuit, DK versus Intuit and HireVue. This lawsuit was filed this year, actually, and what the plaintiff argued is that HireVue's AI-powered video interview software discriminated against deaf applicants and non-white candidates. Now, how HireVue works, the system analyzed facial expressions, tone of voice, and other behavioral cues to make hiring recommendations. But these cues are highly context and culture dependent. For example, candidates who are neurodivergent, non-native English speakers, or from underrepresented backgrounds may be unfairly rated as less competent. And this highlights a very key concern that when companies rely on these algorithms to make hiring decisions, they risk automating and amplifying human bias, potentially violating civil rights laws. And it also calls for attention to the need for transparency and fairness audits in AI hiring tools. Now, this is another case, this time in healthcare. And this case is also inspired by real accounts like that of Sarah Meredith. She's a young woman in the UK who was deprioritized by a liver transplant algorithm, despite being medically eligible. The algorithm was designed to optimize organ allocation and was found to disadvantage certain patients due to its reliance on flawed assumptions about patient urgency and demographics. As a result, Sarah was ranked lower than expected, and this potentially delayed her access to life-saving treatment. This algorithm was found to lack transparency. There was no physician override and no appeals process, as reported by the Financial Times. And just imagine your life or your loved ones' lives being dependent on algorithms. And this is not just fiction. This was happening to real people, and it significantly affected their lives. And this is the last case that I want to cover. Some of you may be familiar with this case. This is actually one of the most widely cited cases of algorithm harm in law enforcement. Robert Williams, he's a black man living in Detroit, and he was wrongfully arrested after a facial recognition tool falsely matched him to surveillance footage of a shoplifting suspect. Despite clear discrepancies, such as blurry and low resolution camera footage, obvious physical differences, there were no actual witnesses, and also his driver's license photo was used in the tool's database without his informed consent. The police treated the system's output as definite. As a result, he was detained in front of his family. He was held for 30 hours until the mistake was recognized. And this case highlights the over-reliance on facial recognition tools, especially when that's being done without proper human oversight and no corroborating evidence. So, as you can see, AI bias is no longer a niche concern. It is making mainstream news. And these aren't just technical failures, they're failures with real human impact. Bias in AI can affect someone's ability to get a job, receive access to fair healthcare, or even avoid wrongful arrest. And it's not just about fairness in theory, it's about someone's future, someone's life, or someone's freedom. And when these stories go viral, they erode public trust in the systems that we engineers build. And since AI is becoming more and more embedded in everyday decisions, so does our responsibility to ensure it's safe and just for everyone. And of course, if this issue is this serious and the impact is this significant, why hasn't the problem been fixed yet? Because tackling bias in AI is not straightforward, because the challenges run deep. And I'm going to cover a few of the challenges in this slide. First, as I mentioned, biased data. AI learns from historical data. If this data is biased, then the AI model is likely going to inherit them. Then the complexity of the algorithms. Models like, for example, deep neural networks, yes, they're very powerful, but they can also be black boxes. There's so many parameters and so many layers to them that it can be difficult to debug or pinpoint where the bias is entering from or how it is influencing our outputs. And then we have accuracy versus fairness, which to me is one of the most significant ones, and it's one of the most highly debated and complex challenges that we see. And I think it's better described using an example. So to begin with, I want to define what accuracy is. Basically, when we optimize our models, we usually aim for accuracy. So basically, how well a model predicts the correct outcome. But this can come at the cost of unfair results for underrepresented groups. So imagine you're a bank and you're evaluating 100 mortgage applications, 70 for men, 30 for women. If you want to aim for demographic parity, then you're going to approve 50% of each group. So let's say 35 men and 15 women. So 50-50, that sounds pretty fair. But this is where accuracy versus fairness comes in. What if the proportion of actually loan-worthy individuals is different across the groups? What if only 20% of men are eligible for a loan? Then we're at the risk of approving less qualified individuals and then rejecting more qualified individuals. And this is where it gets tricky. Do we optimize for fairness or do we optimize for accuracy? And essentially, these are the kind of dilemmas that we deal when we're building real-life applications. Danishta will also cover more on this. And yeah, that's why it's important to, when we talk about fairness, to try to define and contextualize it before we try to measure it. And going back to the challenges, deployment in new contexts. For example, let's say you have a model that is trained, let's say you have a speech recognition model, and that is trained on American English speakers in quiet environments. If you put the same exact model in a completely different setting, let's say in a factory overseas, where it's very loud and people have very strong English accents, the model is likely going to be biased, it's not going to perform the same, and it's going to struggle. And then the last one, lack of diversity, and not in data, but in the people building the systems. Without diverse perspectives, diverse skill sets, diverse backgrounds in teams, we risk overlooking real-world blind spots and are failing to challenge biased assumptions that are usually baked into our models.
Thank you. Before we all head home, throw away our smart fridges and turn off Alexa, let's not do that because we have a few solutions which I would be covering. So bias has existed for a while now. Ever since machine learning models existed, we've had bias. What's different? It's really bias on steroids. Bias at scale. Because the bias doesn't exist in a small model being used by a certain device or a certain department anymore. A higher view example was a perfect example there, that it's at a much larger scale when it gets deployed at a large organization, which is hiring millions of employees or screening millions of employees with the same system. Now, I want to cover the different types of biases coming from data, annotation, model, and deployment. What I'm trying to cover here are the types of sources. Now, the two things we want to compare is the data bias and the annotation bias, and the model bias and the deployment bias. Data bias comes from how the data is collected. Now, let's assume you want to build a fair data set covering speakers from various different accents. You covered 5 speakers from 5 speakers having an Indian accent, 5 speakers having a British accent. You collected a balanced data set, but then it was annotated for emotion detection by a certain labeling lab which defined emotion differently. So even though your data was extremely balanced, the annotation introduced certain differences or biases which got missed. Similarly, model bias versus deployment bias. Model bias can be a result of certain architectures or training recipes, whereas deployment bias could be issues in production, certain components, introducing inputs which completely mess up the result from the model. I'll be covering more in detail about that in the upcoming slides, but just to give an overview of the types of biases here. Dimitra already covered biases coming from skewed data sets and historically baked inequity, so I wouldn't be going over that again. But I wanted to just explain annotation bias in more detail. So here's a very good example. Let's assume we have a data labeling lab, and we're trying to use this data labeling lab to label this sentence, telling your sibling what to do. Now, some labeling folks would label it as very bad, whereas some may label it as very good. Now, if you can see the text clearly up here, certain countries have a culture where it's seen that it's supposed to be very good, whereas some have a culture where it's not. Now, unless we take the diversity of our labeling lab into account, we may not get the exact same results. Similarly, the example I gave earlier for the accent versus emotion, we built a diverse data set containing a diversity of speakers with varying accents and personalities, but then we're having a labeling lab label it for emotions. And based on cultural differences, linguistic differences, the emotion detection may vary, even for the labeling labs, and ultimately by the models, which would be trained by the data labeled by those labs. So treating different things the same can just cause as much harm as treating the same things differently. Now, model architecture choices. In transformers, typically, if you have words like he and doctor together, it may end up learning those patterns as general patterns. And I can go into the nitty-gritty of the architectures that lead to certain results, but 20 minutes is not enough time for that. So I encourage you to connect with me, and in the future, if you ever need information about choosing the right architecture for the right use case, please contact me. I'd be very happy to nerd out on that. But model bias typically comes from how the model learns from that input. Now, deployment bias is coming from multiple places. One of them is prompt-induced bias. I have some examples for that. So mainly, when we write our prompts, when we're trying to use an LLM API, certain text sequences can unintentionally create a bias that we cannot foresee at times. How many of you saw the example of is 0.1 bigger or 0.9 on LinkedIn? No. So there was a particular, I wish I had an example up here, that specific one. It was a popular use case on LinkedIn where certain people were asking ChatGPT if 0.1 is bigger or 0.9, and it responded with 0.1. But to my surprise, when I tried it with a different text sequence saying, is 0.1 greater or 0.9 with more mathematical terms, it gave the right answer. So we shouldn't have to come up with the perfect text sequence to get the right results. But until LLMs get a little better, I think it would be a good practice for a lot of the prompt engineers who use these models day to day, because they're not in research anymore. They're very much in production, on scale, deployed on various different systems. So until we get better models out there, I think writing better prompts is the solution to solving a lot of problems. Pipeline drift. Now, in production, aside from the models, we have a lot of different components which affect the overall results. For example, there was a particular component I can recall which was designed for language detection. And then there were two other models in a pipeline which got entirely different input feature simply because the language detection failed, which was not even a machine learning component in production. So various different components in production where the models are running can often give the wrong input that results in a completely incorrect feature provided to the model while it's running in production. And a lot of those components get completely ignored. Domain shift is when the model is trained for one domain, let's say for the medical use case, but you're trying to use the same model for a completely different domain. For example, fashion. So the jargon changes, the context changes. So domain shift can severely affect, I'm giving an exaggerated example there, but you get the idea. User behavior feedback loops. Now, how many feedback loops come from social media? Which post you liked? A lot of those feedback loops often result in models learning certain biases from the general population, and a lot of them may not be the best patterns to lean towards. Latency and incomplete context. Now, a lot of the real-time models running typically use inputs being built in runtime, which means a lot of times the context may be missing or the input features may be incomplete. For example, real-time audio being processed while, let's say, a phone call is happening. At that time, you don't have the full context because the conversation is still happening in the real time. You still have the first 3 seconds, not enough context. So that can also result in similar issues. Now, I experienced this with Whisper a little while ago. Hopefully they fixed it, but wanted to give an example of a prompt smash. So this is what happens when we use multiple models in a pipeline, and some of them have certain biases. Now, I experienced this with Whisper, that when certain speakers had an accent, for example, an Indian accent, and said something like book a flight tomorrow in an Indian accent, it would transcribe the same exact words in the Hindi script. Or if it was a Chinese accent, then in the Chinese script. Now, the words up here do not write, the words up here are not written in Hindi. It's in Hindi script, but the first word says book, the second word says the third word says flight, and the fourth word says tomorrow. It's just using that the alphabets from that language to build that sequence. So you see how English accent speech got converted into a completely different text sequence. Now we're feeding that text sequence in a completely different language to another LLM model, which may have certain biases towards those languages and may respond differently when the sequence comes in a different language. Result is either the wrong result or a very biased result. So now I'm not saying this happens every single time, but these are the pipelines where things go wrong somewhere along the way, and it's hard to pinpoint when it actually happens. Now, I want to cover bias mitigation for data scientists, prompt engineers, production, and organizations. I would be covering AIF 360 metrics because I feel like they're the best. They're the best regardless of which machine learning algorithm you use, whether you use linear models or transformers. They cover the most basic fairness tests. Now, independence. It means that the model's predictions are independent of the protected attribute. So the bank's credit approval should approve loans regardless of which race or gender the person is from. And independence only works assuming you have the subgroups already identified. So the techniques I'm covering are specifically for situations where you know which subgroups you need to test for. And then we have separation. Now, separation is when you want to make sure all the groups get good accuracy. So, hiring model, candidates from different demographic groups with the same qualifications should have a high success rate. Now, because I wanted to make this more controversial, I thought, let's compare dogs and cats. So, because independence and separation sound very similar, but are extremely different if you look at it closely. So, independence is, do we understand cats and dogs both? Whereas separation, do loyal cats get as high of a loyalty score as loyal dogs? And which fairness metric you choose really depends on your use case. It's not one versus the other, or that you have to use both. It very much depends on which use case you're working with. Followed by that is sufficiency. Now, going back to the cats and dogs example, we don't want to give gold stars to all the cats and all the dogs to make sure the model is fair. So sufficiency makes sure that predictions are still calibrated across the groups. And individual fairness is to make sure similar users receive similar predictions. So if two candidates have very similar profiles, they should receive the same treatment from the model. So I came up with this little cheat sheet depending on your use case. If you're focused on fairness of access, go with the independence score. If you're focused on fairness of outcome, go with the separation score. If you're focused on fairness of trust, sufficiency. If you're focused on capturing hidden edge cases, then individual fairness. And I tried to map the types of bias that can be identified with the types of fairness metric. Now, this is very much generic. This mapping is not exact for every use case, but it will help in terms of identifying which metric can help in your use case. If you have a lot of bias coming from the type of data sets you're building, you might want to start using independence as a fairness metric. Moving on to bias mitigation for prompt engineers. From what I explained earlier, the numbers example, 0.9 versus 0.1, this is an example of how unclear prompts versus good prompts can highly affect the results coming from LLMs. Similar to the number example, you can see how when candidates are being scored with the wrong text sequence, the LLM will automatically respond with the wrong candidates getting higher preferences. OK, now I want you to find this person in this room. I'm serious. It's a very beautiful AI image, but this person is in this room somewhere. Yes. OK, you can reveal yourself. Stand up. OK, so we did a little experiment. There was this one app which was built using GPT and an image generation model named Flux. So typically, you would ask for outfit recommendations, and it would build a detailed prompt using that information, and then provide that to the image generation model. So this is what the user prompt looks like, followed by this is what GPT came up with, and then the final image result, because GPT introduced certain biases from the text sequences it generated, followed by them getting amplified in the image itself. So I guess I wanted to explain more about how multimodal pipelines can sometimes smash things up beautifully, and pinpointing where it happened can take forever to figure out. Now, there are certain metrics for prompt engineering and for measuring toxicity. Again, a lot of details up there. I'd be happy to discuss, but hard to cover because they're very deep concepts. And bias mitigation for organization. Now, this is where we need to see how we can fix these biases on a structural level. And it doesn't happen with one person making a decision on which metrics should be used to analyze these biases or results or evaluation in general. I think the right way would be teams getting together, managers, software engineers, data scientists, identifying which evaluation metrics and which test sets need to be used to evaluate the model. And that would vary based on whichever use case you're working with, which product you're working on, and who your target users are. But working together on a structural level would be the best way of mitigating bias. It wouldn't be just one data scientist telling you which metric to use, or one manager deciding which evaluation set is correct. It really ultimately works when these people come together to identify why that evaluation set works for this product, or why this metric is necessary for this group of people to not be discriminated against. And last but not the least, this is a pretty old topic, but sometimes the best way to avoid a biased AI is to not use AI if you don't need it. Hey, I love AI myself, but thank you. That would be all for my end.